Okay, in Accelerated Math 1, this is Algebra 2 Trigs section 1.5, which is in our unit on functions and transformations. We talked a little bit about this earlier in the year when we did the unit on exponents and logs. So if you're watching this as an Algebra 2 video, things might seem a little bit out of order, but that's not you, it's us. The Excel math people are a little bit out of order. Anyway, the warm-up. This might look a little, again, this might look a little silly if you're Excel 1, but for Algebra 2, this probably makes a lot of sense. Okay, so you can read that there. What's going on with inverses is we're talking about trying to do a function kind of backwards. Let's try to figure out where the output would have come from through a function if we're trying to find the inverse of a function. And if we do that for all of the kind of inputs and outputs in general, we're finding the rule for the inverse of a function. All right, so let's take this warm up seriously. So there's a function that takes an input value, squares it, subtracts 5, and sends out the result. So write an equation, put it in here. So we're taking an input value, it squares it, it subtracts 5, and then the result comes out. So you put in x, and it sends out x squared minus 5. Find the result when the input value is 3. So if you put 3 into this machine, what's going to happen is we're going to take 3 squared and, of course, subtract 5, and we will get 4 out of that machine. So the general concept of inverse here is that let's write a rule that will take the things like 4 and tell us about the 3. Like say what you would have to put in the machine to get 4 will give us what an inverse actually is. Okay, how do we change this result back into input value 3? What operations would you have to do? So to kind of walk backwards through these steps, for the next, that's like the last thing that happened to it was that 5 was subtracted from it. So we would think about adding 5 and then, so we would kind of take that original 4. If we add 5, we get up to 9, and then we'd have to take the square root of that whole thing to get the 3 out. So in general, if we say f of x equals x squared minus 5, what happens here for the inverse of x, and we'll get this notation a lot later, the inverse here would take x as like the 4. Now, of course, the roles of x and y have shifted, and that will become clear as we get better into the notation. But for now, in case you're curious, we took this 4 now, we added 5, and we took the square root of the whole thing, and we got 3. Okay, warm-up number 2. Think of a number, subtract 3, now add 3. What happens? Think of any number. Oh, how about 7? Subtract 3, we get this. Now add 3, we get that. Oh, sorry, that was silly. Add 3. Think about stuff. 3s. Add 3, we get 7. Guess what? We get the same thing back. So this is the idea of, this is maybe a simpler idea of inverses. So if f of x took x plus 3 and g of x took x minus 3, they're inverses of each other. I kind of wrote these in backwards order from up top, but same thing. Those functions kind of undo each other. You get back to where you started if you do one and then the other one. Graph them on the same grid. So if I call this one x plus 3, this is the x plus 3 function. I can fill this out pretty quickly. And looking above at g of x, this is minus 3. This is going to be negative 2 and on up. And if I graph those, I'm afraid this video is going to get too long, so I'll pause for stuff like this. All right, so I've graphed the two of them, f of x, which is x plus 3, and g of x, which is x minus 3. We talked about this in geometry lessons recently, that when functions are inverses of each other, what ends up happening is the two graphs of them ends up being reflections of each other across this y equals x line over there. So if you were trying to make an inverse function, or if you're talking about what is it that's going on with inverse graphs, switch the points of the graph of f of x to get the graph of the inverse g of x. What does that mean by switch the points? It means reverse the x and y coordinates. So like this point down here at 2, negative 1 is on the graph of x minus 3, then guess what? Negative 2, 1 is also on the graph of, is on the graph of f of x. 2, negative 1, so negative 1, 2. Sorry, negative 1, 2 is on the graph of the other one. So in a lesson recently, and I can't even remember if this was in the algebra lesson or in the geometry lesson, but when you reflect things over that y equals x line, the point xy goes to the point y comma x. So if sorry, that's a little sloppy, but graphing those separately, graphing whatever point you graph on the first, on one of the lines, x comma y. If you reverse the coordinates, you'll get the point on the inverse, which kind of makes sense because that's what inverses do. All right, and then the graphs of inverse functions have reflected symmetry over the line y equals x. Okay, make this thing, let's sketch the inverse. Okay, so first of all, we could fill out the table with the reversed coordinates because, again, if we're searching for, if we know the output and we're searching for the input, that's exactly what inverses are supposed to do. I will do all of that. Okay, so there's all the points filled out in the table, just simply reversed from what they were before, and now I'll graph it. Hi, sorry those lines aren't perfectly straight with the equipment I have here, but anyway, that's the graph up there. Is f of x a function? So we're talking about the original black one here. The function, the black line there is a function because it passes the vertical line test. Is f of x a one-to-one function? No, because it fails the horizontal line test. Explained in another section. Is the inverse of x a function? No, it fails the vertical line test. Now this is the red one. The red one fails the vertical line test. And I guess you could probably figure this out pretty quickly, that whenever a function is not one-to-one, then the inverse is not going to be a function. Yeah, pause and listen to that again if you need to. All right, consider this one, sketching out the inverse on the same grid. So to make the inverse of this, essentially, again, what I need to do, and notice this happened again, this is symmetrical over this line where y equals x. Sorry, this is going to be a really bad line. But that's the line of symmetry there, the y equals x line. Same thing here, the y equals x line is going to be a line of symmetry. So if it goes through 0, 0, it's going to go through 0, it's going to go through this 4, 4. Oh, sorry, this is really hard with what I have here to predict where this line's going to go. Oh, no, I'm not going to try. Actually, if I go faster, it's not so bad. Anyway, that's a line of symmetry. The other way we're going to get, and notice on the other page, to get points on the inverse, all we need to do is reverse coordinates. So if 4, 4 is on there, then guess what? 4, 4 is also on the inverse. 0, 3 becomes 3, 0. Negative 1, negative 1 becomes 1, negative 1. Negative 3, 0 becomes 0, negative 3. And 4, negative 2 becomes negative 4, negative 2. Something like this. Okay, see if I can connect these dots and not have anybody throw up in the seasickness. Okay, do you notice reflective symmetry over y equals x? Well, yeah, you're supposed to, so good. Is g of x a function? So that's the original black one. Yes. Is it one-to-one? Yes. So guess what? The inverse is also a function. Okay. If a function is one-to-one, then the inverse is also a function. And if it is a function, we call the notation for the function, and I use this above, the little -1 subscript. In the Excel class, you've noticed we've done that already when we did the sine, cosine, tangent, or in your geometry class, you did sine, cosine, tangent, and that was a same kind of notation. Okay. Consider this set of points. Let's plot those. I will pause so you don't have to suffer through that. Okay, there they are. Now, this isn't any kind of connected dots or anything. It's just those are a set of points. State the domain. Well, the domain would be all the x coordinates. So 4, 2, 7. It's just these numbers. It's not like an interval or a range or anything. And the range is all the y coordinates, -3, -1, 0, 4, and 10. Does this set of points represent a function? The answer has to be no, because if we use the input of 2, 2 goes to -1, and 2 also goes to 10, and that's a problem. That makes this thing not a function. It's like 2 can't have 2 different birthdays, if you remember the analogy I used in class. Find the inverse of the set. Well, the inverse of the set is just all the points written in the backwards order. -3, 4, -1, 2, etc. So there you go. State the domain of the inverse. Well, guess what? This is just going to be reversed from before. So this is all of the x coordinates now here in the inverse, which should look exactly the same as the range above. And guess what? This happens also. So this is now the range of the inverse. Is the inverse a function? Okay, so do all of the x values in this list only lead to one y value? Well, yeah, because we only have one of each there. What do you notice about the domain and range of the inverse compared to the original set is that they just change places. Okay, proving functions are inverses. Okay, there's 2 ways that they may ask you to do this, or ask you to kind of evaluate if there's an inverse relationship going on. This one goes back to the original kind of purpose and definition of what is an inverse in the first place. An inverse is an undoer, right? Like an inverse is a function that's going to take you back to where you started from. Or if you knew an output of a function, it's the inverse that's going to take you back through that trip and get you back to the input of that function. So if you take the output of a function, immediately stick it back into this other thing you think you might be the inverse, if it takes you back to where you started in the very first place. So here we are starting with 2. 2, we put into the x plus 3 function, it turns into 5. Now we think of 5 as an input to the x minus 3 function, and guess what? It brings us back to 2. So if we get the same output that we started with at the very beginning before you even put things into f, then yeah, it took us back home, sort of. Since f and g are inverses, it also works the other way. So notice on this first one here, they're doing f of g of x, or we're going to put it into, g of f of x. We're using the f machine first and putting that into the g machine. Here we're using the g machine first and putting it into the f machine, so this is f of g of 2. Put 2 into the x minus 3 machine, becomes -1. Then we turn around and stick -1 back into the x plus machine, and guess what? We get 2. So f of g of 2 is also 2. So when both of these things happen, we can be pretty sure that this is going to work. This is an inverse function. Of course, we know this right now. All we've done is shown that this works for the number 2. It might not work for all numbers. Well, we know it does. But this isn't enough to prove in general that these things are inverses, so just know that. But this is a demonstration of what should happen with inverses. What happens when x equals 0? Well, guess what? It's always going to continue to take us back home. So like f of g of 0 is going to equal g of f of 0, which is going to equal 0. And the same thing would happen with 5, etc. So since we cannot possibly test all input values, we just have to prove their inverses more generally using x as an input. So if we put x in, and if it turns out, and you could do it with this too, we're going to do it with more complicated ones. If you can simplify f of g of x, and you can simplify it down and realize that that's always going to be x, and if it works the other way, if g of f of x is always x, then you've just shown algebraically using function composition, because that's the language of the assessments, that they are inverses. Okay, so let's use function composition to verify. Like I said, there's 2 different instructions here, so make sure you keep this straight. This says using function composition to verify. f of g of x is like using the kind of overall f structure, of x. Handwriting is really hard on this. But instead of x here, we're going to use in general the rule of g of x. And you're going to use more in composition in 1.5 plus 2. So I just use this overall structure, but instead of this x, I put in g of x. Okay, so let's simplify this now. F of g of x, this is 1/3 times that mess. If I distribute the 1/3, this is going to become x minus 2/3 plus 2. Yeah, I think I did that right. 1/3 of g of x plus 2, right? Okay. And that's turning out to be, oh, I forgot an x in here. Oh, no, I didn't. I'm fine. This turns out to be something weird, right? This is like x plus 1 1/3 or something. That is not x. So if that turns out to be not x, so I put something into the g machine, I put that into the f machine, I don't get where I started, then no, these turn out to be not inverses. It's kind of a mean first example to give you, but that's what turned out. Like, and you might think these are inverses. Like if you're trying to make an inverse out of 1/3 x plus 2, you might go, okay, instead of dividing by 3, I'll multiply by 3. Instead of adding, I'll subtract. Like it actually doesn't work because the functions don't take you back to x when you compose them. Let's try. I'll leave that there so you can see it. Let's try this one here. What's f of g of x here? Of g of x here is, we're going to take the function f, but instead of x, we're going to put in all of g of x, 1/2 x minus 2 plus 4. That turns into be, if I distribute that 2, I get x minus 4 plus 4. Okay, this is looking better. That turns out to be x. So I know that if I put anything into the g function and then take that output and put it straight into the f function, it turns out to be what I started with, which was this original x. But technically speaking, I have to test it the other way because, you know, there's some things that don't work out quite right all the time. There's domain restrictions. We'll talk about that later. But to be ultimately sure, I want to do this the other way also. I want to put f into the g function. So I'm writing the g function, but when I get to x, I'm going to actually input all of this f of x expression, okay? Minus half, or sorry, minus 2, and I get, if I distribute the half, I get x plus 2 minus 2. It looks very similar, and yay, we have inverses.